Welcome everyone to the RQI Construction Working Group 3 seminar. Today we have Zixuan Liu telling us about joint work with Ognjana Reshkov entitled Parity Erasure, a foundational principle for indefinite causal order. Zixuan, we're looking forward to your talk.
Okay, so thank you and Catherine for inviting me to give this seminar, and also thank the other organizers of this seminar. So I'm very happy to share with you the recent work by me and Ognian. So our paper is available on arXiv. You can find it on arXiv. So in this paper, we ask some foundational questions about the notion of indefinite causal order. So here, I first give a brief introduction to indefinite causal order. Conventionally, we assume a quantum process to have a well-defined causal structure. But when we assume quantum theory only locally, the assumption of causal structure is not necessary. So actually, we can find higher order processes which are not compatible with any well-defined causal order. So here in this picture, I show like a bipartite one, which is also higher order quantum process is also called a supermap, quantum supermap. So in the bipartite case, it transforms two channels into a valid channel. So for any choice of channel A and any choice of channel B, the supermap creates a valid quantum channel. And some of the supermaps are not compatible with a definite causal structure, and this is called causal non-separability. In the bipartite case, we cannot find a random mixture of fixed order process. We cannot find such a decomposition. So here, the fixed order process can be realized by the standard quantum circuits. So here in this circuit, Bob Alice precedes Bob, so Bob cannot signal to Alice. And in this one, in the green circuit, Alice's operation is after Bob's operation. So here Alice cannot signal to Bob. So a canonical example of indefinite causal order is called the quantum switch. So here, instead of choosing either a fixed causal order, Alice before Bob or Bob before Alice, quantum switch can create a coherent control of the order of the two channels according to the state of a qubit. So here, for example, if Alice perform a unitary gate U and Bob perform a unitary V, if the control qubit is set to K0, then the order of the gates is U before V, and if the control qubit is set to K1, the order of the gates is V before U. So it actually produce a controlled version of U and V, VU and UV. And it is also a process that has been tested in laboratories. So the idea of quantum control of causal order can be generalized to multipartite case, and the most general one is called QCQC. So that is quantum circuits with quantum control of causal order. So another example of indefinite causal order can be is demonstrated in a theory independent way called causal inequalities. So they are like analog of Bell inequalities. The most general higher order process is described by the process matrix formalism proposed by Oreshkov, Costa, and Bruckner. In their work, they find device independent certification of indefinite causal order. So they construct a higher order supermap. So here we refer to it as OCB process. So they find with OCB process and some local operations, they can generate probabilities which are they can generate probability distributions that are not causal. So here in the level of correlations, the causal constraints means some no signaling condition. So if Bob cannot signal in a setup where Bob cannot signal to Alice, then the marginal probability distribution of Alice does not depend on Bob's setting. And in the other direction, Alice cannot signal to Bob, then Bob's marginal probability distribution does not depend on Alice's setting. And the OCB process cannot be understood as a random mixture of the causal correlations. So this is also a theory-independent certification. It does not rely on the formalism of the theory. And in this work, we are trying to find out some information-theoretic aspects of the correlations with indefinite causal order. So one of the motivations is to search for information theoretical principle or operational principles which explain the correlation with indefinite causal order. So in general, we find in previous works we have found process matrix correlations are not algebraically maximum. So for example, in the guess your neighbors input game, if both Alice and Bob generate a random bit and they are required to guess each other's bit, and in this game, with the most general process matrix strategy, we find that there is some non-trivial upper bound. So no matter which process matrix you use, which instrument you choose, the success probability of the game is strictly upper bounded by some non-trivial probability. So currently, this upper bound may not be tight, but it still tells us there is a non-trivial upper bound. And until now, we still have no information theoretical principle to explain such non-trivial bounds. This is very different from Bell scenario. In Bell scenario, we know at least the correlations unsatisfy the no signaling principle. So Alice cannot signal to Bob, Bob can signal to Alice, and more generally, and more precisely, they also satisfy. We can find quantum correlations also satisfy some other principles such as information causality. So it can to some extent recover the boundary of the set of quantum correlations. However, when we consider the signaling scenarios, when we consider the scenarios with process matrix formalism, we cannot find some analogy principles. And another motivation for our paper is that we've actually the scenario causal inequalities has some limitations. For example, if you consider some process like quantum switch, you can find if you use the black device independent test by just observe the correlations, then the correlations you find is always causal. So it means that actually the quantum switch can only generate causal correlations, and these correlations are compatible with well-defined causal order and can also be generated by classical processes. So the shortcoming of this type of test is one of the shortcomings is that the non-causal and non-classical features are hidden for some processes. Actually, it has been proved that for every QC can only generate causal correlations. So there is some limitations with this method, and we cannot certify the features of indefinite causal order in this way. There is some way around this method. So by considering some by considering causal network network self test. So here they instead of using the previous the simplest device investigation, there are some protocols which can certify the indefinite causal order in quantum switch using a spatially separated party. So here the party is spatially separated, space-like separated from the others. So it creates like it creates some like interplay of Bell non-locality and the indefinite causal order. So in these protocols, in these protocols, they have found the certification of indefinite causal order in a device independent way. And in the work by Van der Laat, Barrett, and Kubeler, they found like some theory independent inequality similar to Bell inequality. And also this was found by some other people. And in the paper by Duo and Abbott and their collaborators, they found a way similar to self-testing. So they can self-test the state of the party P using some technique from self-testing of entangled states. So in this way, they can verify indefinite causal order from the correlations. So something has been overlooked in the previous study of indefinite causal order. So previously we only treat like local party as a single node. So when we consider black box certification, black box test, every party can choose an arbitrary instrument, and the instrument is regarded as a black box. So one of the shortcoming of this approach is that it overlooks the causality inside each laboratory. So in process matrix formalism, even if we assume the causal order can be indefinite, but in local laboratories, standard quantum theory holds. So in local laboratories, actually the process matrices or supermaps preserves the local causal structures. So here we propose to consider scenarios in which every single party there is some structure in the local operations. There is some fine-grained structure inside each node. The simplest structure locally is to consider some sequential instruments. So here, as you can see in this picture, so in the first party, we consider a sequential of instrument A and C. So in this test, the player first choose a setting for A and get an outcome A1. Then he choose a setting Y1 and get a setting B1. So here we explicitly formulate some causal structure in local laboratory, and the local validity of causality implies that the outcome of an instrument can influence the setting of a subsequent instrument, but the converse is not allowed. So this means that, for example, here in this laboratory, the outcome obtained in the first instrument can be used to at the setting of the second instrument. So there is some causality here. And it also means like this setting Y1, the second of the second instrument cannot influence the outcome of the first instrument. So Y1 cannot influence A1 and Y2 cannot influence A2. And so this has like a direct consequence. The direct consequence is that this type of experiments actually simulate a classic process, classic supermap. Um, because for any A1, we can connect we can insert a classic channel between A1 and Y1 and also insert a classic channel between A2 and Y2. So in this setup, actually we can interpret the setting and the correlations as a classic supermap. So as you can see in this picture, you can so this correlation actually transform some probability distributions from classic channels into classic channels. So it means that this product always defines a valid probability distribution. So when you compute the product of the correlation and any choice of local classic channels, you will get a valid probability distribution. And here we provide some information-theoretic characterization for these type of correlations. And since every locally causal in correlations can be understood as a classical supermap. So here we find an information theoretical principle for these type of correlations. Actually, this principle characterizes supermaps. So here, if we have a supermap described as these probabilities, then in the bipartite case, we can find and here we assume like here if we assume we suppose the settings Y are uniform random bits and then we fix the setting X. So here X is a list of settings of the first instrument. Y is a list of settings of the second instruments. If we set Y to be uniform random bit and fix X, then we get a probability distributions of A, B, and Y, and we consider the marginal probability distribution of A. When we consider the marginal probability distribution of A, we can find some independent conditions. So firstly, since because A1 is from the first instrument and Y1 is from the second instrument, so these two random variables are independent of each other. Because Y1 cannot assign to A1 and Y are uniformly random. And similarly, the condition we have the independent condition between A2 and Y2. And what is interesting is that if we consider the joint distribution, we find that the joint variable A1 and A2 is independent of the parity of Y1 and Y2. And this is for the bipartite case, and we can generate this property to arbitrary number of parties. So if you have many parties, you can select an arbitrary subset of them, and the outcome of this subset is independent of the parity of y in these cases, and also we can generalize the property in which y are not binary. They can be arbitrary of arbitrary dimension. To formulate parity ratio, we can choose an arbitrary function which encode the random bits into the setting y. And in fact, the condition here, like we can define we can always define a valid probability distribution is equivalent to the parity ratio condition. So this is an information theoretical principle because it can be understood as a communication task. So here you can consider like the task is to communicate the random bits y, the vector y, the settings y to the outcome a. So the constraint from a local causality is that the outcomes a has some independent conditions with the variables y. And here are some examples. Here are some examples. In the bipartite case, it is simple because we know that it has been proved by Oreshkov, Costa, and Bruckner in the OCP paper. They proved bipartite classic supermaps are causally separable. So in the bipartite case, classic supermap cannot have indefinite causal order. Either they can be understood as some random mixture of the process with like A before B or B before A. So in either case, one of the bit y and y1 has to be lost. So as a result, we can see their joint outcome is independent of the parity of the two bits. And also we can observe check this in some cheaper so here I provide a process called Lugano process. In this process, the outcomes this is a deterministic process. So the outcomes can be computed from the settings. So here you can see like in this is a valid process matrix because valid classical supermap, as you can see. So here like A1 does not depend on X1, and also A2 does not depend on X2. A3 does not depend on Y2, Y3. Sorry, A1 and Y1. So and also you can consider the parity of A1 and Y2. They does not depend on the parity of Y1 and Y2. So these are so here we have provide intuitive and information theoretical principles for classical supermaps. The application of this property is to characterize quantum supermaps. So here we can consider a special case of locally causal experiments. The special case of locally sequential experiments is that you do some independent operations A and C. So here A is like a P is a PV measurement in quantum theory is described as PVM. And then after this PVM, the experimenter prepare some state as output. And also the other parties also did the same. So in this type of test, we can actually this is actually local tomography of the supermap. So you can view a supermap as a channel which maps the output to their input. So the local process tomography is a procedure which prepares states locally and then do some measurement and also do some measurement locally. So from the data, from the correlations, we can identify the supermap. So in the supermap can be represented in this local process tomography representation. And since the LPT procedure is a locally sequential experiment, they must respect the validity of the local validity of causality. So it means that for these type of correlations, we can also connect A1 to Y1 with the classic channel, also connect A2 to Y2 with the classic channel, and they can be described as a classic supermap. They satisfy the parity erasure condition. And moreover, actually, we can prove that this property determines the set of process matrices. So if you consider the set of multipartite channels, process matrix corresponds to exactly to the two channels that respect parity erasure. And so this result is actually does not restricted to quantum theory. So we can consider supermaps in general operation probabilistic theories. So in the general probabilistic theory, we can formulate similar channels, states, instruments, all these notions we have in quantum theory. But they do not assume the formalism of quantum theory. They do not describe the state space as operators on Hilbert space. So in this general probabilistic series, we can also define like higher order transformations similar to process matrix formalism. Here we consider a series which has some basic probabilities, like for example causality. It means you cannot signal from future to the past. Formally, it means the outcome produced during the preparation of state is independent of choice of measurement subsequently performed on it. So in a sequential instruments it means the previous the outcome of the previous instrument can influence the settings of the second instruments. And also we consider a property called the local tomography. So it means the joint state of multiple systems can be constructed from local measurement data on each system. And another property is called the one-way signaling decomposability. So this is a property of bipartite channels. So if you for any bipartite channels, if there is no influence condition from one system, one input subsystem to through an output subsystem, then we can realize this channel with some explicit connections. So here is the circuit, one-way signaling circuit. If B1 cannot influence A1, then the channel can be realized by connecting a pair of channels. So in this channel, there is a slot from A1 to B1. So This property holds in many theories, including classical theory, quantum theory, and any causal operation probability theories with local tomography and purification. We in this paper we show that okay, the parity ratio parity ratio condition actually characterize the set of supermaps. So every supermaps can in this class of series can be understood as a channel that respect parity ratio. So here I make a conclusion of the results of this paper. This is a very short paper, and in this paper we propose a new paradigm for testing quantum processes. In this paradigm, we consider a sequential instruments in each laboratories. So this new paradigm may allow us to observe explicitly some principles of indefinite causal order. So in particular, we found one called parity erasure. It can be derived from local validity or causality. And using this principle, we show that in a large class of series, valid supermaps are those and only those whose local process tomography representation respects parity ratio. So here are some. Here I concluded with some future outlooks and future directions we can gain from the results of this paper. So in this paper, we consider a new paradigm in which in the local laboratories can have some fine-grained structure in which the operations are connected into circuits. So this may lead us to think of like some a new type of black box certification of indefinite causal order in the quantum, for example, in the quantum switch. We can consider some operations, local operations with some structure, and then probably from the correlations from these type of correlations, we can certify indefinite causal in the quantum switch. And also, it might give us some ideas to find out to compute the upper bounds of to find the upper bounds for the process matrix correlations. The existing method for computing upper bounds is based on some special correlations, and maybe using some insights from parity ratio, we can find the new methods, or maybe we can find some operational principles which constrain the process matrix correlations. And in the end, this new paradigm may provide some insights into the development of cyclic quantum causal models. So previously there has been a few works which trying to interpret supermaps at some causal formalism, causal mechanism. They can by generalizing causal model to cyclic ones. So here and also in the previous study of cyclic causal models, they regard the local operations as a single node, as a single operation. So maybe if we introduce some structure in the local operations, perhaps we can bring some new insights into the development of cyclic causal models. So this is the end of my presentation. I thank you very much for your attention, and I'm happy to answer your questions.
Thank you very much, Zixuan, for the nice talk. Let's see if we have any questions already.
Maybe I can. Hi. Maybe I can ask you if you can explain a little better how you characterize the channels, parity erasure channels. So I understand that's a device-dependent characterization of process matrices, right?
Yes, this is like a theory independent characterization of process matrices.
Oh,
So we
okay,
can
I thought it was theory dependent. So this is still theory independent.
theory independent, yes.
Okay.
So we can do this characterization in many theories satisfying these properties. So you can see in our paper. So actually, we can characterize process matrices as parity erasing channels. So previously, we for general process matrix, we can use like something like to write it as like a tensor product of Pauli channels, Pauli matrices, or something, or channels which are which are either identity or traceless. Um, and there is also another way to express these constraints as partial trace. So it's like a process matrix can be understood in quantum theory can be understood as an operator in some subspace. And so here parity erasure gives some information theoretic meanings, give the information theoretic understanding to this subspace. So the channels cannot be an arbitrary one. It has to satisfy some signaling constraints, and the signaling constraints is given by the parity erasure conditions. So in the paper in the proof of these results, we make use of the one-way signaling no decomposability. So if one party if there is some no inference condition from B1 to A1, then we can decompose the channel into a circuit. So it can probe arbitrary channel from A1 to B1. And here, if the channel, if the multipartite channel is parity erasing, and we insert arbitrary channels into this dot, we still get a parity erasing channel for the other parties. So we can do it recursively. So we can
The question is if you can explain a little more, what does it mean parity erasure channel?
Okay, so in this definition, so here I did not. You can check in our paper. Parity erasing channel. Our definition is that we do a local process tomography of the channel. You can choose arbitrary. You can choose arbitrary preparation and measurements, and you can get a local process tomography representation. The channel is called parity erasing if the LPT representation satisfy the conditions here. Or in other words, channel corresponds to a process matrix if and only if the local process tomography representation correspond to a classical supermap. So does it answer your question?
I think I have some questions, Fabio. Maybe I can try to make some more specific questions in this. Could you go back to that slide when you talk firstly about the parity erasure? Yeah, there. I'm a little confused at what is your definition. And so could you explain me better what you mean by A1, orthogonal to y1. It's like a1 orthogonal to y1 given x, or a1 is orthogonal to y1 given x. You understand? And also better to understand better what are these conditions, it's a bit fuzzy for me.
So okay, so here we consider like because classical supermap can be described as the correlation here, and we trying to characterize classical supermaps with the constraints on the correlations. So here you can understand it as a classical channel from XY to AB, and so there is some constraints on this classical channel. So here we trying to create a probability distribution by choosing the setting Y to be uniformly random bits. So here the settings Y you can see is the settings of the second instruments. So it's output of the in the local laboratory. Y1, Y2 are the in the classical supermap are the output of the other outputs, and then
there you are referring to the bottom figure.
Yeah.
Okay.
Yeah, because the first one induces the second one, the above one induces the bottom one. So here we're trying to interpret the restrictions on classic supermaps as some communication restriction. So if you view it as a channel which trying to communicate Y in the settings Y to A, and here we in this communication we choose Y to be uniformly random bits, and we choose an arbitrary X. So here X is fixed. So here that's what we mean by the condition on X. So if you fix X, then you find the random variable A1 is independent of random variable Y1. And similarly, you can find some other independence of the random variables.
Okay.
And what is interesting is that this type of independence is equivalent to their definition of classical process matrices. So the correlation transform classic channels into classical channels if and only if in this communication task, the outcomes and the settings satisfy these independence conditions.
Okay, I think I got it's a new concept for me, but now I think it's clarified. And
oh yeah, okay. Maybe I did not mention it here, but you can view them as a special type of random access code. So here, for example, you can encode the data Y1 and Y2 into the process into the supermap, and then you can get some states, and these states satisfy some conditions like called the parity erasure. So there is one bit of information is lost from the states if you choose Y1, Y2 to be uniformly random bits, and so there are 2-bit information. But from the A1 and A2, from the decoding procedure, you can only at most obtain 1-bit information, because the parity of the Y1 and the Y2 cannot be accessed from is lost, is erased by the supermap.
Okay, I think I will not fully understand it now because the new concept, but it's much clearer. Thank you very much for explanation.
Yeah, thank you for your question. And yeah, I think also I think this one is a little tricky to present. So, but if you start from the random access code idea, if you know random access code, then probably you have some ideas. Like a random in a standard random access code, if you encode is to encode 2 random bits into a single qubit. So the dimension restriction has to erase some information of the 2 bits. So if you can, if the encoding allows you to decode the first bit perfectly, then there is no information about the second bit. This is similar to the case here. In these local sequential experiments, if one of the bits can be decoded perfectly, then it means there is a perfect causal order. There is a well-defined causal order. So the next party can retrieve the bit. But if there is a definite fixed causal order, then the other bit is lost because if Alice precedes Bob, then Alice cannot receive the bit from Bob.
Well, I thank you very much for your detailed explanation. Maybe I think Tim has a question. Timothy, do you want to make a question?
Yes, sorry, I have a question as well. Sorry, there was some bug on my side. Yes, so maybe follow up on this question of random access code. So here in this slide 11, but also in slide 10, just before that, let's say A2 can be dependent with Y1, for example. You can still have cross dependencies, or can you not?
Yes, A2 can depend on Y1 and A1 can depend on Y2 depending on the if you choose some for example, if you choose the fixed causal order between party 1 and party 2, then party 1 can signal to party 2, and if you choose the converse order, then party 2 can signal to party 1, and if you choose a random mixture of the 2 causal order, I think both A1 and A2 can depend on Y2 and Y1 respectively.
Yeah, that's what I figured. So that there is some extra thing about interpreting as a random access code. It's some kind of delocalized random access. And I'm wondering, especially with respect to the picture here in slide 10 you're showing, how important it is that the supermap S is not acting in between A and C operation and it's not acting on B and D. Like, is it just something of your drawing that the supermap is not acting between the box A and C and B and D, or is it can?
So okay, I think you have this question because previously you have a work with Organian about multi-round process matrices. So it has a similar picture like this. So in the multi-round process matrices, the supermap can do something between A and C and also do something between B and D.
Exactly.
I think the parity ratio also holds in the multi-round process matrix formation. Because in the multi-round case, you also assume local validity or causality. So there is there is no causal order between the 2 parties, but for the operations of of a single party, there is a well-defined direction of time, and so there is some fixed order locally. I think if you consider the 2-round process matrix, you can also obtain a parity ratio condition on the correlations.
Yes, I wonder how the condition then would be equivalent. Like, is the supermap in blue you've drawn a specific kind of multi-run process matrix, or is it more general than a multi-run process matrix? That's an interesting question.
Yeah, it's more general. It's different. I would say it's different from multi-round case. So here this is something because previously like in the previous study of indefinite causal order, we always consider the local operations as a single one. So you have a single setting and a single outcome, and in this case, we consider something. We separate the local operation into a sequential one. So in this one, we can observe something called causality, like explicitly we can see the effects of the causality constraint, because here y1 cannot is equal to a1 in the local laboratories. And an important difference from this and the multi-round case is that this is a single round process. So the communication between party 1 and party 2 is single round. It means that they cannot do something like guess your neighbor's input perfectly. So for example, in the multi-round case, you can do it guess your neighbor's input perfectly by first like A can signal A can be before B, and so Bob can know the setting x1, and then Bob's setting can be communicated to Alice in the second round. So in this case, they can win the guess your neighbor's input with certainty. But in the locally sequential scenario, we have only a single round of communication. So in this case, they are still constrained by the one round bounds. So whatever instruments they choose, they cannot win the guess your neighbor's input with certainty. I think this is very different from the multi-round case, and it cannot be simply derived from the multi-round case by imposing some causal constraints.
Yes, thanks a lot. This is a great answer. Explains a lot. Thanks.
Do we have any further questions? If not, then let's thank Zixuan again.
Yeah, thank you very much for your attention and your questions.
Thank you very much for accepting the invitation.